Welcome to The Explainer. You've probably heard about quantum computers and how they promise to solve these huge, impossible problems. But here's the thing, they run on a totally different kind of logic. So today, we're going to crack the code, the actual math that makes all that magic happen. Yeah, this is the big one, right? The central puzzle of the quantum bit, or qubit. How can something be in two opposite states at the exact same time? Well, the answer, surprisingly, isn't really in the physics. It's in the math. A special kind of math that just happens to be perfect for describing this exact problem. Okay, so first things first, we've got a challenge. If a state isn't just a simple 0 or a simple 1, how in the world do you even write that down? We need a way to capture, the proportions of each possibility. And the tool for that? It's something called a vector. Now, the best way to think about a vector is like a recipe. Seriously, it's just a simple list of numbers that tells us the exact ingredients, how much 0 and how much 1 are mixed into our quantum state. So check this out. For the state we call 0, the vector is 1, 0. What's that mean? It's 100% 0 and, well, 0% 1. Makes sense, right? And you guessed it, the state 1 is just the opposite. 0, 1. Simple enough. Okay, but this is where it gets really cool and powerful. A superposition, that mix of states, it isn't some brand new complicated thing. It's just a new recipe. In this vector, those letters, alpha and beta, they're just the weights, the amounts of state 0 and state 1 in the mix. Suddenly, we can describe any possible combination. All right, so we've got a way to describe a qubit state. That's step 1. But a computer doesn't just sit there, right? Its whole job is to process information. So the next big question is, how do we change these states in a really precise, controlled way? And the answer is, you guessed it, another math tool, the matrix. In the world of quantum computing, you can think of matrices as quantum gates. They're like these little transformation machines that take in a state vector, do a very specific thing to it, and then spit out a brand new one. You know what? Let's actually try this out. Let's set ourselves a mission. We're going to take a qubit that is 100% definitely in the 0 state, and we're going to use one of these gates to put it into a perfect 50-50 mix of both 0 and 1. And the tool we're going to use for this job is the famous Hadamard gate. You'll hear about this one a lot. This matrix, its whole purpose in life, is to create a perfect, even superposition. It is the ultimate state mixer. So how does it work? Well, applying the gate is a really clear mathematical process. You take the gates matrix and you multiply it by the states vector. The rules of the math, linear algebra, they take over from there, and what pops out on the other side is a new vector, and that represents the qubit's brand new state. And voila! Here's the result. Our definite 0 state has been totally transformed by that Hadamard gate into this new vector. And what does it represent? A perfect 50-50 superposition of both 0 and 1. Mission accomplished. Okay, this is all great, but this math can't just be a free-for-all, right? For it to actually describe the real world, it has to play by some pretty strict physical rules. So what are the fundamental rules of this quantum game? It really comes down to two key rules. First, on the left, you've got orthogonality. That's a fancy word that just guarantees our basic states, 0 and 1, are totally, completely distinct from each other. And second, on the right, you have normalization. Think of this as the reality check. It makes sure that the probabilities of measuring a 0 or a 1 always add up to 100%. No more, no less. And we can actually prove this with the math. There's a calculation called the inner product, which is basically a way to measure the overlap or similarity between two vectors. And for our 0 and 1 states, guess what that overlap is? It's exactly 0. They share absolutely nothing in common. That's what makes them orthogonal. And this right here, this is the absolute core of that normalization rule. Remember those alpha and beta values from our recipe? When you square them, you get the actual probabilities of measuring a 0 or a 1. And those probabilities must always, always add up to this number, 1, 100%. This one simple rule is what keeps all this abstract math tied to real things we can actually measure. All right, let's take a step back and zoom out. We've seen all the individual pieces of the puzzle, so let's put them all together now and see the whole big picture of how this mathematical language actually works. So the whole process really breaks down into the 3 steps we just took. Step 1, we use a vector to describe where the qubit is starting from. Step 2, we we use a matrix, our quantum gate, to transform that state into something new. And finally, step 3. We make sure the result plays by the rules, like normalization, so that it actually corresponds to a valid physical reality. So when it's all said and done, what's the big takeaway here? It's that this stuff, linear algebra, it isn't just some abstract math concept that you learn in a class. In this world, it is the toolkit. It's the foundational language we use to model, to manipulate, and to tell the quantum world exactly what we want it to do. So we've done it. We've cracked the code. We've learned the language. And that leaves us with the only question that really matters now, and it's the most exciting one of all. Now that we know how to speak to the quantum world, what are we going to build with it?